My name is Andrew Wang, an assistant professor from Temple University. I'm the presenter of Faure, a practical approach to network analysis, which was collaborated with my first-year PhD student Fangping Lan and Bing Gui, also from Temple. The past decade witnessed significant progress of network analysis, as shown by this partial list of publications, as well as events and news from academia and industry. And the result is various verifiers that are capable of answering questions about reachability, consistency, and more. These analyzers borrow ideas from diverse fields like testing, simulation, model checking, and more. And what is common to all of this is a comprehensive evaluation process that expects definite knowledge of the network input that is expected to always output a decisive answer. Such a complete approach is not surprising. In fact, this is a salient feature of formal analysis. But in this talk, we argue such a complete approach may not be the best fit for the networking domain. First, we argue that the network input we are interested in is not a single definite one. Rather, it is all possible data plane instances produced by uncertain events produced by interacting control protocols. So when uncertain environment is presented, shall we just repeat the analysis as practiced today? A second mismatch we observe is that our knowledge of the network input is oftentimes limited. On the global internet, visibility into the network is constrained by administrative boundary. And even within a single domain, the verifier is constrained by performance. It may not always have the latest information. So when unknown information is presented, shall we accept the verifier to stop working entirely? This talk prevents a Faure system that attempts to address both. For uncertain environments, we propose lossless modeling, a partial model that directly models uncertainty itself that is capable of uncorrupted answer. For partial information, we present relative complete verification, a new type of verifier relative to the level of information allowed to it, that is also allowed to output I don't know, but I don't know only when more information is necessary. Let me show you the idea of lossless modeling by an example. Consider faster rerouting on toy topology here, where the backup links will be used on one primary fail. Obviously, different failures will produce different forwarding tables, which in turn can be queried and produce different reachability tables R. And even on such a small example, repeated reachability analysis can be exponential. So we borrow idea from incomplete database using a structure called C-table. In C-table, we introduce variables x, y, z, which allow us to encode the failure scenarios that allow us to encode all the possible forwarding instances once and for all. What's more important is that the C-table representation can also be queried and produce the reachability table in another C-table that also captures all the possible reachability results. Such a nice feature, we call it lossless, because the answers that can be obtained on the partial representation in C-tables are not distinguishable from the answers that can be obtained on the definite instances. That is, the difference between the regular representation and the C-table representation are not visible to the query. So the remaining question is, in what language shall we write the query? One naive choice is SQL. An extension of SQL to C-tables does exist. But SQL was designed for ad hoc data retrieval, not for static analysis. And for this reason, we turn to the logic-based cousin of SQL, datalog. An extension of datalog, as far as we know, does not exist. So our first contribution is to create a datalog extension, which we call Faure-log. The main idea in the formalization of Faure-log is to distinguish between variable occurring in the C table and the variable used in the datalog-like rules. They are different because variable in the C table stand for unknown values, whereas variables in the program are used to deriving new facts. And once we make this distinction, it becomes clear how to extend the evaluation function that gives meaning to datalog. In the same way, we can give meaning to Faure-log. For more details, please see our paper. And here is a pretty standard recursive query that allows us to obtain the retrievability table from the following table we've seen earlier. And here are more examples illustrating the power of Faure-log. Observe how various complicated failure patterns can be specified in a compact, natural way in Faure-log. For more details, again, please see our paper. Now let me show you relatively complete verification. Recall that a relatively complete verifier can also output don't know, but only when more information is absolutely needed. And this allows us to construct a complete verifier out of a sequence of verifiers or tests with increasing power. Each takes more information and outputs more answers. The specific design, of course, of these tests depends on the particular knowledge available to them. And next, I want to show how Faure-log makes this vision possible. For example, consider a toy network here. We have a verification team responsible of verifying invariants continue to hold after updates. Additionally, there are some other teams managing and maintaining constraints about the network. When the verification team is only allowed to talk to the other teams, but not access to the network, the only information available will be the other constraint, and only mechanism available is subsumption. Now, if the verification team is also able to access the network updates, then maybe the verification team can also incorporate these updates into the reasoning process by rewrite. Next, to see how Faure-log can handle subsumption, we first encode the constraint and target invariants into a zero-array Faure-log query program. The idea is the corresponding constraint or invariant is violated whenever panic was produced. This allows us to reduce subsumption to program containment, a standard problem in datalog, which can be further reduced into simple valuation in Faure-log. The intuition here is that we can prove, on this concrete example, CS contains T1 if CS produces panic whenever T1 produces panic. That is, more generally speaking, we can verify P1 contains P2 if applying P1 to the instance of P2 always produces panic. For more details, please check our paper. When the network updates become available, we can also make use of them by applying a datalog rewriting process in Faure-log, allowing us to use that updated information during Faure-log reasoning. The overall intuition is that we can verify a property after an update by checking its modified version before the update. And more detail can be found in our paper, which also shows a practical implementation and promising performance. And we think there are significant improvements that can be made. To recap, we examine the mismatch between the complete network analysis approach and the networking domain, and we argue for departure from this complete approach, proposing lossless modeling and relatively complete verification. As a realization of our vision, we also present the Faure system, in which Faure-log language was proposed to enable querying about uncertain environments and analysis of partial information. Thank you.